Welcome back everyone. So this is the next topic in our syllabus. It is flow between parallel plates. See, this concept is almost similar to the pipe flow concept. See, pipe we had this thing, it's a pipe, flow goes inside and there are pipe walls. Here it's almost identical. Here you have two plates and between these there will be flow. So what almost 90% of the concepts we use there we'll be using again here. Now let's go into the derivation part. So this is the diagram of our consideration. The distance between these two parallel plates, that is the thickness, is T, and we are considering a small element. The same way we consider over there in pipe flow, we are considering same here a small element A, B, C, D here. The length of that element is delta x here, and the thickness, that is breadth, here we call it as thickness, is delta y. So as I already mentioned in last class regarding pipe flow, only two forces we will be considering. Two forces we will be dealing here. That is, one is pressure force, another is shear force. Here pressure force acts in these directions and there will be shear force in this direction tangentially to the element we are considering. Now earlier we considered a 3D element. Now what we are doing is, for the sake of making the calculations easier, we are taking the width of this element as 1. Width is equals to 1. See here, in x, in length, what do we get? Length is equals to delta x. Height or thickness is equals to delta y. The breadth or width here is equals to 1. There we took it as delta z, but here we are taking as 1. This is to ease our calculations even more. So now on face AB, the force acting is, see this one, face AB, we have this pressure into area, that is force is equals to pressure into area. We have on face AB the force is equals to P into area. What is area? P into delta y into 1. See, delta y is, see, for pressure is acting on this particular surface. Since the thickness is delta y and we are assuming the breadth as what? 1. We'll have area is delta y into 1. Similarly on this face, this value into delta y into 1. So on face CD is equals to P plus dou P by dou x into delta x into delta y into 1. Delta x here is coming because since pressure only changes in the x direction, it won't vary along the y direction. And coming to the shear force value, here we have tau, and similarly tau into area, that is delta x into 1, is acting on this particular. Since this is not a cylinder or circle, the area here will be simple. You can directly see, and whatever is there, that is the area. And similarly here also, tau plus dou t by dou y into delta y into delta x into. Why these values are coming? Dou p by dou x, dou t by dou y, we've already seen that. If you have any doubt regarding that, comment in the video. I'll explain it to you again in case if it is needed. So now, what is the shear force shear force. It is the phase that is acting on BC. Shear force on BC is equals to tau into delta x into 1. Similarly, on AD we have tau plus dou tau by dou y into delta y into delta x into 1. Since there is no acceleration, we are considering steady uniform flow. What are we considering? Considering steady uniform flow. This is still a laminar flow only, steady uniform flow and laminar flow. Since there is no acceleration of the fluid, the force, because we know F is equals to ma, Newton's second law. If acceleration is equals to 0, why is acceleration 0? Uniform flow. Uniform flow means no change in velocity with respect to time. So we get acceleration is equals to 0, which means the net force acting on the fluid element is equals to 0. This is why we equate pressure and shear forces summation to 0. On all these phases together, here pressure force, there is one in this direction, there is one in this direction, there is one in this and one in this. So summation of all these forces is what we'll be dealing right now. So applying the principle of equilibrium, what we get? P delta y into 1 minus P plus dou p by dou x to delta x into delta y into 1 minus tau into delta x into 1 plus tau plus dou tau by dou y into delta y into delta x into 1 is equals to 0. From this what we get? This value, this and this value multiplied, they get cancelled. This value and this multiplied, they get cancelled. So in the end what we get? Minus dou p by dou x to delta x delta y plus dou tau by dou x, dou tau by dou y to delta y delta x is equals to 0. We send one of this element to the other side and this get cancelled. What will we get? Dou p by dou x is equals to dou tau by dou y. We got a similar equation in flow through circular pipe also. Now from this we already know shear stress tau is equals to mu dou u by dou y. We'll apply that here. Dou p by dou x is equals to dou by dou y of mu dou u by dou y. What will we get? Dou p by dou x is equals to mu into dou square u by dou y square. Means dou square u by dou y square is equals to 1 by mu dou p by dou x. This is the relation we are getting by applying this particular equation. From this we'll see what is the expression of velocity. There we got a expression for velocity, u is equals to 1 by 4 mu into minus dou p by dou x into capital R square minus small r square. In the same way we are going to derive an expression for velocity over here also. Let's see how it is done. So dou square u by dou y square, we integrate. By integrating we get dou u by dou y is equals to 1 by mu dou p by dou x to y plus c1. Again integrating, what we'll get? u is equals to 1 by mu dou p by dou x into y square by 2 plus c1y plus c2. Since we assumed, sorry, not assumed, since dou p by dou x is only in the x direction, there is no change in the y direction, whereas velocity changes in the y direction. See, in pipe also we dealt with the same thing. As the distance from either wall increases, velocity increases, because at the walls velocity will be 0. Now we got a raw equation sort of thing here. Now to get these values C1 and C2, we have to apply boundary conditions. The same way we applied over there, we will be applying boundary conditions over here also. What are the boundary conditions? Boundary conditions. See, we know at walls velocity is 0. That is at y is equals to 0. Y is distance from the wall, the distance from the bottom wall. So at y equals to 0 means at this particular point, that is here. This, see here in diagram also it is mentioned, this is y. The distance from the bottom wall is y. If y is equals to 0, it stays on this wall. So at y equals to 0, what happens? U is equals to 0, because at wall velocity is 0. Again, there is another wall that is on top. There also velocity is 0, but there y becomes t. Why? Because t is the thickness. The distance of the top plate from the bottom plate is t. So at that point again velocity is equals to 0. First we apply u equals to 0 value. 0 is equals to 1 by mu dou p by dou x into, again y is 0 here, 0 by 0 square by 2 plus c1 into 0 plus c2, which means c2 is equals to 0. We apply y at y equals to t, u equals to 0. 0 is equals to 1 by mu dou p by dou x, what is y here? T square by 2 plus c1t. Again we already know c2 equals 0, we are not going to apply that. From this what we'll get? c1t is equals to 1 by mu into minus dou p by dou x into t square by 2, which means c1 is equals to minus 1 by 2 mu into dou p by dou x into t. We'll substitute this value in this equation. What we'll get? U is equals to 1 by 2 mu dou p by dou x to y square minus 1 by 2 mu into dou p by dou x into ty. We take common terms, what will happen? We'll write as same as we wrote there, whereas we got 1 by 4 mu into minus dou p by dou x, right? So we'll write in that same form only, 1 by 2 mu, take minus common, minus dou p by dou x into ty minus y square. This is the equation for velocity, that is velocity distribution in a flow between two parallel plates when both the plates are at rest. That both plates are at rest is important here, because even if one plate goes around with another velocity, then we can't apply both the boundary conditions. The boundary conditions will change. So now we have dealt with velocity distribution and all. Earlier we saw that velocity was parabolic. We got a, if we draw a pipe like this, there we got velocity, this is the center line, velocity varies like this, whereas shear stress varies like this. This is the zero value for shear stress, this is the maximum value for velocity. In here also it's the same value. This is Vmax, that is velocity is maximum at center and zero at the walls, and shear stress is maximum at walls and zero at center. These are two important terms. No matter where you go, for flow between a pipe, inside a pipe, between plates, these terms are important. This is first point, this is second. Okay, now we saw all this stuff, we know whatever it happens. Velocity varies parabolically, shear stress varies linear. So this we already saw in the pipe flow itself. Let's go about finding maximum velocity. To find maximum velocity, what will we do? V max at center. Center means here y is equals to t by 2. This changes. In pipe we saw small r is equals to 0 at center, whereas here we are taking it as y is equals to t by 2. Let us apply this value y equals to t by 2 here. So what will happen to u? U is equals to 1 by 2 mu minus dou p by dou x to ty, t into t by 2 minus t by 2 whole square. What will happen? 1 by 2 mu into minus dou p by dou x into this t square by 2 minus t square by 4. T square by 2 minus t square by 4, that is equals to t square by 4. Finally we will take out this 2 also, we can write it as 8, 1 by into t square. This is maximum velocity for flow between parallel plates. Now, same, we'll again continue the same process. We'll find out the ratio between these two. U max by u is equals to minus 1 by 8 mu into dou p by dou x into t square by minus 1 by 2 mu to dou p by dou x into ty minus y square. What will we get? Mu goes, dou p by dou x goes, this goes 2. U max by u is equals to minus minus also goes, so t square by 4 by ty minus, we'll take 4 downside, 1 by 4, 1 by ty minus y square by t square. So u max by u is equals to 1 by 4 into t y by t, 1 by y by t minus y by t whole square. Write this a little bit, minus y by t whole square. This is the value of u max by u. If we write u in terms of u max, u is equals to 4 u max into y by t minus y by t whole square. This value here is not that important as it is in pipe flow. There we have a proper relation. There we got 1 minus small r by capital R whole square. That is what we got the second term as umax into 1 minus small r by capital R whole square. Here we are getting y by t minus y by t whole square, all this stuff. It is important here also, but there it is even more important. We have to remember that equation there. Here just see how it is derived. So this ends the first part of this lecture. The next continuation part, we will derive equations for discharge, pressure difference and shear stress. See you.